the talk of Professor Ernst Eberlein from Freiburg University, and maybe Albert Nikolaevich speak some words.
No, I want to say only the following. Ernst is our very old and very good friend. And so we're happy, ready to listen to hear him and to see him. Ernst, please start.
So thank you, Albert. Now let me try to get on the... Do you see now the first slide?
Yes, yes.
Yeah, very good, very good.
Okay, okay.
And before your talk, I would like to speak some words about our tradition. During your talk, please all participants have stop your cameras and microphone. But if you would like to ask a question, to give, you can open your microphone, and your question may be during the talk of Professor Eberlein, not only end of the talk, but during of the talk. It's our tradition. Thank you very much. We can start.
Thank you. So I have 60 minutes. Is this correct?
Yes, 1 hour.
1 hour. Yeah, so first let me say that this is a big pleasure and a big honor to present this work in your United seminar in Moscow. It is, what I present is joint work with 3 other people, with Laura Ballotta from Bayes Business School in London, Thorsten Schmidt, he is my successor here in Freiburg, and Rachid Zainedine, who was a visitor at the Institute for Advanced Studies, the FRIAS.
Where Laura now?
Sorry?
Where Laura? Laura now in England or in Germany?
Okay, okay.
Okay.
Yeah, before I go into complex life insurance products, maybe it's a good idea to recall what a classical life insurance contract is. Already the name life insurance contract is somewhat misleading, because life, of course, plays a certain role, but certainly not the most important role. The most important, it's about retirement. You want to accumulate some funds which you can use after retirement. And the classical contract is organized in the following way. You pay when you are still young, for example, when you have 35 years and got a permanent position, then you spend either a lump sum or you accumulate over the years a certain capital which contributes to the funds which you have available after retirement. Classically, this is 65. Of course, I know in the Moscow people do not retire at 65, but here it's a typical age where such a contract matures. And the key feature is that the insurance company is guarantee a number of things. They guarantee a certain interest rate, a certain return on this money, which you give them to manage. And of course, this is a very attractive feature, because if you go yourself to the stock exchange, you do not have any guarantee. You can lose a lot of money if you are not very successful with managing the funds. But the key point is, how high is this guarantee? In the good old times, actually exactly account until 1986, this guarantee rate was 3%. This is fixed by the government, by the supervisors. Then it climbed to 3.5 and finally even to 4%, since we had a lot of inflation in the 80s. to compensate that, this guarantee had to be raised. But after the year 2000, this guaranteed rate started to go down. And where is it now? Currently, it is less than 1%, it's 0.9%. And starting January 1st next year, it will be 0.25%, that means 0.25%. And of course, once you reach that point, this classical scheme is no longer very attractive. I mean, we have a certain inflation. The ECB is accepting 2% inflation. That's their official policy. And if you get only 0.25% guarantee, then you might say, why should I sign such a contract and bind myself for a very long period of 30 years, let's say. Now, here is where, I should be a bit more precise about this guaranteed rate. This is actually the maximal rate which you can offer as an insurance company. Why are the supervisors, the government, in other words, interested to fix such an upper limit? Now, it's evident. I mean, you could cheat. You could offer your insurance clients, the policy holders, a return of, let's say, 5% or even 6%, then everybody would be eager to sign such a contract because that's a very high return. But what would happen? The insurance company would not be able to earn such a rate at the financial markets. And so they would go bankrupt as soon as the first contracts mature. And to avoid that, to protect the customers and to protect also the insurance companies, this rate is fixed by the government. But of course, this maximal rate has to be offered by every insurance company. Otherwise, if you offer only a lower rate, people might go to competitors and might not sign a contract with you. So what can be done to offer you attractive life insurance? The solution is not to go into the fixed income market, the interest rate market, but to invest your funds in the stock market. If you take an index, for example, let it be the DAX here in Germany or the S&P 500 or even a worldwide index like MSCY. So in this case, you can expect that you are connected to the growth of the whole economy. And at the long run, even if it goes down for 1 or 2 years, at the long run, it will increase. Eckhart Platen has written a lot about these long-term developments of indices. And this is what you want to exploit. But you want to keep, of course, some of the guarantees in addition. Otherwise, you could go yourself to the stock market and invest in a fund which tries to simulate the index. Now, what do? We go into variable annuities. Variable annuities produce a post-retirement payoff, which is connected to a broad market index like the DAX, the S&P 500, MSCI, etc. And this way you have a chance to participate in the growth of the whole economy. The whole economy, these are we, the citizens. And at the long run, we expect that this economy grows. Now, this has a certain history already. The US sales in 2018 were, the contract size were 100 billion. And these contracts are signed by guarantee seekers, people who want certain guarantees on one side and participate in growth on the other side. And this is particularly interesting in the current low interest environment. Now, of course, the insurance companies who offer such a product have a certain risk, and they have to design the contract in such a way that this risk is manageable and can be hedged. And on the other side, of course, they have to respond to what the customers want. There is a very large variety of different contracts, but they have one common feature. This is this guaranteed minimum X benefit. And this X stands for a number of things. For example, accumulation benefit, withdrawal benefit, death benefit, etc. If you are interested to see a whole classification of this contract type, there is a beautiful survey paper by Bacinello, Milosevic, Olivieri, and Pitacchio, where they show how broad the spectrum of these contracts is. Now let me be a bit more specific. We will concentrate on this guaranteed minimum accumulation benefit. And this means that you have a certain guarantee, a floor, which might be, for example, 1% return or 2% return. That would be a lot already. And you compare it to the return of a reference fund, typically the index, like the DAX. And what you get in each period, for example, in each year, is the better of the two, either the minimum rate, the floor, or if in case the fund produces a better return, then you get credited this return. Typically, there is a cap on the return. You do not get it all. That makes it easier for the insurer to reduce the risk. So you might cap if the return is very high in a specific year, you might cap it at 5% or 6%, for example. So this is a ratchet mechanism, a mechanism where returns are credited annually or every 6 months to the policyholder, and then they are locked in and you cannot lose them anymore. No, if you are not familiar with the word ratchet, ratchet is a technical device, a wheel which goes only in one direction. If it tries to go backwards, then it's stopped by the mechanism. And that's what we have here. Now, from the mathematical point of view, it is nothing, as you will see in a minute, as a structured portfolio of options. And for this guaranteed minimum accumulation benefit, the source of the risk is, of course, the behavior of this reference fund. A second feature, which makes life more complicated, is the so-called surrender benefit. The customer, the policyholder, might be interested to terminate the contract during the lifetime. So if you have a contract starting at age 35, maybe at age 45, you have the idea, oh, I want to buy a house, and you don't have the funds to buy a house. So you remember that you have this contract with the insurance company, and you might want to use the funds, terminate the contract and use the funds which you have at that time point and finance your house. So typically the insurance company is not very happy about that. So they charge you a certain penalty to avoid that too many people terminate contracts prematurely. So the risk for the insurance company is this lapse behavior, as people say, that people stop the contract before maturity, and that creates a liquidity risk for the insurance company. Now, this is the most difficult part to model because there is not enough data. The insurance companies keep their data secretly, they don't make this public. And if you have to model it, you typically need expertise knowledge. Finally, and this is what justifies the word life insurance contracts. Of course, there is a death benefit. In case you pass away during the life of this contract, the money is not lost. Your heirs, which is typically your family, will get the amount which has been accumulated up to that point. And here is the point where biometric risk, mortality risk comes in. So what we do, we discuss this wretched variable annuity. This is a prototypical example. Many other contracts can be modeled and analyzed along the same lines. We will discuss modeling assumptions. We will develop a stochastic model, a hybrid model based on dependent time inhomogeneous Levy processes. And we will discuss valuation and computational issues. And now let us look at some features of the contract. So now we go into mathematics. Let me describe this accumulation benefit in mathematical terms. First of all, we have a notional. This is amount like notional of a bond price, typically something like 100,000 euro. This should be invested into an underlying index via some fund. Now we have a time scale. Let's say capital T is 30 years, and you look at dates at the end of each year, and you determine the return which the underlying fund earned during that year. That means you compare the value of the underlying fund at the beginning of the year to the value at the end of the year, and you divide by the value at the beginning of the year. So this is a certain return, which can be negative, of course. Now what we need is a random time in case the policyholder wants to terminate prematurely, and we need another random time, namely the remaining lifetime of an X-year-old individual. Of course, the probability for dying depends on the age when the person starts the contract. So in mathematical terms, the payoff at maturity from here in 30 years, let's say, is the notional multiplied with a certain increase factor, which is the maximum for each period. It is the maximum of this guaranteed rate, and the return, actually one typically multiplies the return with a certain factor, a participation factor, let's say 80%, then the psi would be 0.8. And the return is also capped, as I mentioned already. So this is the amount which you get in case you are still alive. That's this indicator. And you did not terminate prematurely. Now, these horrible expressions for mathematicians can be written in a much nicer way. Namely, it's evident that this is equivalent. The increase factor is for each of the periods, and there are n periods, it's a minimum rate f. In case in one of these periods, the return multiplied with this participation rate is higher than f, the minimum rate, then this is credited, it increases this factor, but you do not get it all. What is beyond the cap has to be subtracted for each period. So you see, we are back at an expression which we understand quite well, because this is nothing but the payoff of a call option. Still, you have this indicator function, which make life much more difficult. Second benefit, the surrender benefit. We get into a second time scale, for example, also at the end of each year, or let's say every 6 months, you're allowed to terminate the contract. The insurer will apply a surrender penalty This is a factor between 0 and 1, and typically it's not a constant, but it is going down to 0. If you terminate the contract very early, then you get a high penalty. If you terminate it close to maturity, this is close to 0. And for the purpose of this contract, we decided that the surrender is the underlying value, so that's the value of the underlying fund, penalized with this factor if you get out of the contract at time point TJ bar and if you are still alive. Finally, the third benefit, the death benefit, enters with a third time scale. Typically, the fact if you are still alive is monitored by the insurance company, let's say every month or every 3 months, and the payoff is just what you get in case if you stay until maturity, with the exception of the last fraction. If you die during this interval with the index I, then you get the minimum rate. So again, we have ugly indicators here. And of course, this term can be decomposed in the same way as we did it already with the accumulation benefit. That means we have nothing but call options here. Oh, that was the wrong direction. Now we have to model the dynamics of all this. We have a lot of dynamics here. Let me start with the fixed income market, with the interest rates. In such a long distance contract, it doesn't make any sense to work with two simple models. For example, to work with short rate models. The classical models are short rate models. Maybe I show you that picture here. Here you have the term structure of interest rates for 30 years. The interest rate you get depends on the time, how long you can invest your money. Unfortunately, currently we still have negative interest rates here for a time up to 15 years in Euro country, in the ECB world. I took this picture last week. You can find them on the EC webpage. And the approach which we choose is not to model the short rate. The short rate models just take care of this end, of the lower end of this curve, and all other points here then depend in a deterministic way on the dynamics of the short rate. So the Heath-Cherrow-Morton approach is one which modeled immediately this whole curve. So this is something which moves now dynamically. For example, here I took the November 2nd, that's a red curve, and then it had moved down already to November 4th. And so there are three basic movements. There are parallel shifts, there are twists, it goes down at one end and up at the other, or vice versa. And finally, there are changes in concavity. And of course, the real movement of these interest rate curves are combinations of all these three basic movements. Now, actually, I took also the forward, the instantaneous forward rate. This is the object which we model, and we will not use the classical Heath-Cherrow-Morton approach with Brownian motion as a driver. We will use a much more sophisticated approach, namely we use time inhomogeneous Levy processes as drivers, which allows us to create a more realistic environment than you would get with Brownian motion. Here are the movements from November 2nd to November 4th for this curve. And this is what is taken as a basic quantity here. And in interest rate theory, it's different from equity theory. In equity theory, you know what you want to model. It's basically the stock price or the index. But in interest rate theory, you typically have a choice. What you take as the basic quantity you want to model and which quantities are derived from that. And we take here the so-called instantaneous forward rate as the basic quantity driven by a time inhomogeneous Levy process, which is given by the cumulative function. You can easily transform this into the dynamics of the bond price. The bond price is just x of minus integral FTT integrated with respect to maturity, integrated with respect to the capital T. So you start either with this quantity or with this, that's the same thing. Actually, in the paper in 1999 with my student, Sebastian Reible, we started with the bond prices and derived the instantaneous forward rate, but in the later papers with other students, and in particular with Jean-Jacques Cotte, we started with instantaneous forward rates. So this is the first thing we have to model. Then we need a model for the index or the stock price. Now there we take the classical approach. We take value at time 0, time x of, this is the discount factor, x of integral of the short rate. The short rate is FTT, where capital T equals small t. So this is the discount factor. Then we have a random term, and we do not take here just non-time dependent volatility. We have to take a time-dependent volatility that gives you more flexibility. I should say that here in interest rate theory, it doesn't make any sense to use a constant volatility because the volatility of interest rate products goes down when you approach maturity. Stocks don't have a maturity, but these instruments have a maturity. And when you get closer to maturity, there's less volatility because you're sure to get your money. Now, in addition to this random machine, we built in an expression which is driven by the interest rate Levy process. This helps to create dependence between the two. It's well known that there is some statistical dependence between the stock market and the fixed income market. And we model this by building here a term which has the same driving process. And now we want to make sure that we are in a no arbitrage setting. That means discounted stock prices have to be martingales. So take the discount factor on the other side. Then we have these two random terms. And now you have to choose this drift such that it exponentially compensates these two stochastic integrals. And that's easy to do. We always work with deterministic volatility structure. So these integrals are still processes with independent increments. And if you have exponential of a process with independent increments divided by the expectation of exponential of these processes, you get a martingale. So this is easy to determine such that the discounted stock price is a martingale. The same applies here. So this drift term drops out immediately once you use the same argument, which I explained, and then the drift is a function of the cumulant and the volatility function. Surrender model. We need a model to get the stochastics of this surrender behavior. So as I said, this represents a major risk for the insurance company because of liquidity issues. If somebody wants his money back, this is invested So the insurance company has to create the corresponding liquidity. Why do people terminate a contract prematurely? Now, there are two basic reasons which are discussed in the literature. First of all, there are personal reasons. As I mentioned already, you decide at some point, I want to buy a house and I want to use the funds which I accumulated to help to finance this house. Or the second reason are financial opportunities. So this is the so-called interest rate hypothesis. If you are familiar with what the financial markets can earn for you, you might realize at some point, if I invest the money which I have in the insurance contract myself in insurance products, I'm better off. And this is the so-called interest rate hypothesis for stopping the contract. The probability for surrender will be modeled via a surrender intensity approach, which has two components. First of all, it has a constant, and by this constant, we try to get all these personal contingencies. That's very difficult to get into statistically because the data is not available. So expert knowledge is the only way out of that. And then for the interest rate hypothesis, we consider the following process. You remember that we have a guaranteed rate, which in the discrete setting before was given by F. Now we go in the exponent, we go into continuous time. So this has to be transformed into a continuous time guaranteed rate delta. And we look into what do we get when we terminate the contract at time t. That is, the return is ln st, the logarithm, penalized. So remember, this is a function between 0 and 1. So the logarithm is a negative term. This is subtracted. And we invest then these funds into the interest rate market at the current rate. So this is what we get for the remaining time from small t to maturity capital T. And we look now into this spread between the guaranteed rate and what we could earn when we reinvest the money in the fixed income market. And this process now is made even more flexible by applying a non-negative function to it and also a dependence parameter. So we can manipulate this parameter, how strong we want this spread to go into the surrender intensity. And then the probability for surrender is modeled as exponential of minus integral this intensity process. Finally, we have biometric risk, the risk of mortality. So if you model the random time describing the remaining lifetime of an X-year-old person, then the survival probability at time t is given by this expectation, which is an expectation based on an intensity. And here we use a very classical approach. We did not invent anything new here. So one of the classical approaches is that you take the initial curve, which you can observe now, model it via the Gompertz-Mackerham model that's given here with the parameters B and Z. And then you know that this is not a stationary quantity. Mortality has changed over the years. In the Western world, people get older and older. We have quite a number of people now with 100 years. And so far, even with a pandemic, there is no change visible. So you have to have a certain random factor for mortality improvement. And this is modeled here by such an Ornstein-Uhlenbeck process driven by a third Levy process. In the implementation, which I will discuss at the end, this is just a Brownian motion. So the basic assumption here, and that's very important for the analysis, that we assume independence of democratic and financial risks. This is what in the literature is done. Now we are ready to value such a contract. We use the usual risk-neutral valuation principle. So we take the payoff at maturity, discount it to today's value, and take the risk-neutral expectation. The same with the surrender payoffs. Now here we have a sequence of payoffs along this ladder of time points, and we have to add them up. And the same with the risk of dying, the death benefit. This is also a time scale, and we add it up across this time scale. And these three events are exclusive, so the value of the contract is just the sum of these three expectations. And to get now these values, many mathematicians stop at this time, at this point, and say, oh, I have an expectation, and don't worry about the rest. Now the real thing you have to do now, how do we get these expectations? And this is via Fourier Techniques. So let me make a little excursion now to an older paper. First of all, Fourier Techniques, of course, have a long tradition in mathematics, but in a paper which we finally published in 2010, we use this technique since the 90s already, but finally we ask, what are the real mathematical assumptions which one needs that this works? And this was published in 2010 in this paper. There's a second paper where we consider path-dependent options. So we want to price an option with a payoff phi depending on the whole path, and we use as a model for the underlying quantity S0, the value now, x of a Levy process or a time inhomogeneous Levy process. And the key property which we exploit is that we are able to separate the underlying process from the payoff function. Let's look at a standard example, a fixed strike look-back options. Albert likes this look-back option. He has published on that. So what is a look-back option? So in a usual option, your payoff depends just on the value at maturity. And you might regret that you did not sell it before, because before maturity had a fantastic value, and at maturity the value is either zero or not what you expected. So a look-back option considers the whole path of the underlying and takes the best value, the supremum, compared to the strike. Now, of course, such an option must be very expensive. So you might be not very happy to pay a very high price for such an option, but as an example, it's a very good example. So what you see here is that we have a function e power x minus strike, positive value, and in this function we feed in the underlying process, which in this case is the supremum process. It is not necessarily just the driving process of your model. And the payoff now can be written as a function f of the driving. We push the starting value as 0 in the exponent. This is very convenient. And then the time 0 price is the risk neutral expectation of this payoff f of xt minus s. And this can easily be massaged via Fourier-based methods. Let me denote by mxt the moment generating function of xt. The payoffs very often are unbounded functions. This is unpleasant for this purpose. So you have to bring them down via a dampening factor, e to the minus rx. And let's denote with L1bc, the bounded continuous functions which are integrable. And one of the assumptions in this paper, one set of assumptions is this, that the dampened payoff is in L1bc. For this dampening exponent r, the moment generating function is finite, and the Fourier transform of the dampened payoff function g is integrable. This is only one set of assumptions. We have a number of them. In particular, we have higher dimensional versions as well in the paper, which we will need for this purpose here. And then you have the following theorem. If these three assumptions are in force, then the value can be written, I better go to the next picture, as well, the starting value goes in terms of the logarithm, that's a small s, and the other two components which go in is the characteristic function of xt at some complex value, so that's the x-axis shifted by minus ir, and the Fourier transform of the payoff function taken again at a complex value. And this is easy to prove. Here you have this integral over the payoff f. You transform it into an integral with respect to the dampened function g. And now you remember, due to that assumption C3, you can invert the characteristic function of the Fourier transform of g. You plug this in here. You change the order of integration, and for this you need these integrability assumptions. And then what you discover here is nothing but the characteristic function of xt, and we transform the g back into the f, and then we get in the complex plane, and we have a nice integral. So the payoff functions which you usually have to deal with, like a call or a put, can easily be integrated. So these are the Fourier transforms. By the way, it's the same for the call and the put, but the r is different. For the call, you have to choose the r bigger than 1, and for the put, the r has to be chosen non-negative, as a negative, yes. Another example are digital options. For this, you need already different assumptions, which you find in the paper, because this is an indicator function, which is not continuous. Double digital options, the same. We have discussed many examples in this 2010 paper. And the other ingredient, which you might think is very complicated, very often it is not. Let's look at the case where the process is just the underlying process L. Now the case is where you have to consider infimum or supremum along a certain time interval. This is something where the Wiener-Hopf technique comes in, the Wiener-Hopf factorization, fluctuation theory for Levy process, etc. And this is in the second paper from 2010. But typically we take as Levy processes generalized hyperbolic models. And for these, it's very easy to get the characteristic function. First of all, you do not need the characteristic function for an arbitrary time point capital T, because you just need the the t exponential of the time point 1. And the time point 1 is characterized by the generating process of the generating distribution of this process. And this is just a quotient of normalizing factors. Let me explain how, let me use a gamma process to explain how simple this is. So if we compute the moment generating function for a gamma process, so here is the integrand, here is the density, and now you see we have here a linear term in the exponent and here a linear term in the exponent. You put this together, then it's no longer the right density process for a gamma distribution. So you have to create this artificially by multiplying with c minus u power gamma. You divide by it again. Now you have a density. The integral is just 1. And then you have the corresponding expression for the characteristic function, just taking it at IU. So usually this is not magic to get the components. Having said this, I can present you now the result for these non-trivial payoff functions. So first, the guaranteed minimum accumulation benefit. It looks awful, but it is not. Of course, the analysis is several pages in the paper, but here you see what goes in. First of all, because of these independence assumptions, the survival probability is here as a first term. Then here is the bond price. Here is the notional I, and here is the increase factor, how this notional increases. It's 1 plus this guaranteed rate multiplied with such a Fourier integral. And here you have just the same for these options. This is the participation factor. And then you get a certain term, which is again nothing but such a Fourier integral. This is for the guaranteed rate, and you have to subtract the corresponding amount for the cap. The same applies, it's actually much simpler for the surrender benefit. Here you have just the notional amount, the penalty factor, then you have the survival property and the difference of two Fourier integrals of the type which I introduced. And finally, the death benefit looks awful, but it is not, because here you have to separate first the time points before the first surrender possibility, then all the time points until the last possibility to surrender, and then the time points beyond that last surrender possibility. So what is very important here is that all these integrals are very high dimensional, and the dimension is determined by the number of time points for surrender. So if you have a 10-year contract, let's say, and you have 9 surrender time or 10 surrender time points, then here it's a 9-dimensional and here is a 10-dimensional integral. So this is now a question of numerics. So you have to integrate high dimensional functions. And if you look into the standard packages, which the computer programs offer you, you will realize that dimension 3 is the highest you can use. Anything beyond dimension 3 is unpracticable because of the high computation time, if it can be handled at all. And so we use Monte Carlo integration. Don't mix it up with Monte Carlo simulation. We do not simulate any path. That's hopeless in this context. We use Monte Carlo integration, which replaces such a high-dimensional integral by just a sum, and we use importance sampling in order to make it faster. And yes, importance sampling, of course, you have to choose the sampling distribution wisely. I show you a picture. This is in dimension 3, which is of course completely unrealistic here. The sort of integrals which shows up depending on this function h, which we have in the surrender intensity. Now in the intensity 1, where the h is x squared, you get something which looks a bit like a normal, multidimensional normal distribution. Whereas if you choose h being the absolute value, it's a much steeper function. So it's a bit sort of Cauchy density. And this is why in the numerics we use here for importance sampling these distributions. To implement this model, we chose normal inverse Gaussian processes. So we have 4 parameters. This is the cumulant function. It's very simple. For the driver of the mortality improvement ratio, we took a Brownian motion at driver because this is standard in the literature. So we, as I said, we did not invent anything new here, but you could as well take a Levy process driving this. And then you get an explicit expression for the survival probability. And this allows you then to get real numbers out of it. Here are the numbers. Now, this hybrid model for the financial risk, where you have a dependence between stock prices and the interest rate market, was developed in this paper with my student Markus Ruthmann, which is published in 2018. And we took the parameters, the financial parameters from there, because calibrating to the financial market is another effort, but it is done in this paper already. So we could take the Levy parameters from that paper. We took Vasicek volatility function. So we have 2 driving processes to model here. And what is the contract? We chose for simplicity a notional value of 100. In reality, you want something like 100,000 as a notional. We took a 10-year contract. We took 1% guaranteed rate, the F. Now it's not exactly 1% because we want the continuous time analog to be a nice number. So it's a bit more than 1%. The cap rate is 5%. Returns beyond 5% are given to the insurance company to finance this whole thing. We took a participation rate of 70%. And this is the penalty function, which goes down to 0. The 2 time scale for accumulation and for surrender are 1 year. And the time scale for monitoring death is 6 months. Here are the parameters for the surrender model. And we took the mortality parameters from another paper. This is Escobar et al. From 2016. And now we are ready to get real numbers. So for this 10-year contract, the value of this guaranteed minimum accumulation benefit is 83. The value of the death benefit is 12. The value of the surrender benefit is 15. That means the value of this contract, that means how the insurance company can sell it to a potential customer, is 111. You see, of course, the CPU time is highest for the death benefit. That's clear because you have many terms which add up. Now, if you take a different function h in the surrender modeling, then you get slightly different values for these three components, and the total value is not that different. We looked a bit into sensitivity. That's important for the insurance company when they offer such a contract. They have to understand what is the influence of this participation rate and what can we do with the cap. So we studied these two parameters which go in, which is quite interesting. Here you see a graph. If the cap rate is 5%, that's the blue line, then the dependence on the participation rate psi is not very impressive. It doesn't change a lot, the value. If you go to 7.5% cap, then it's already a bit more depending on the participation rate. And if you have no cap at all, namely cap 20%, the return will never be more than 20% unless you take something like BioNTech as your underlying, they earned billions this year. Then the dependence is very strong on the participation rate. So these sensitivity results give the insurance company some information how to choose these parameters. Of course, you can offer several parameters to the customer and you can ask him, what do you want? So let me summarize. We developed a general framework by discussing a prototypical type of contract for such complex life insurance products. And we solved the problem how to get the numbers out of it by using high-dimensional integral techniques. This is a paper. It has been accepted by Insurance, Mathematics, and Economics and is there online already. When it appears in print, I don't know. And if you are interested in the basic technology, of course, there's a classical reference, Shakot-Sheyaev, but something which is more adapted to mathematical finance is our book from 2019, which I show you here. And let me stop here. I think I'm just in time. Thank you.
Dear Ernst, thank you very much for your excellent presentation and talk. And now we have time for questions, please. Maybe some comments, questions.
Sorry, it was written on slides that H is symmetric function. In what sense it is symmetric?
Oh, like the parabola, x square or absolute value. Actually, this is not a very strict assumption. You could separate the two halves, but it would make things more complicated.
Mm-hmm. Thank you.
I mean, the justification for the symmetry is what I said before. There are two basic reasons for surrender. You could surrender if the spread, which is fed into this function h, is very high. That means if the interest rate in the market currently is very good for you, and that could be a reason to terminate the contract and to invest yourself into the interest rate market. But another reason is the opposite. If the spread is very low, then you might be interested to take advantage of very low interest rate and refinance something. So both sides could be a motivation for you to terminate the contract, and that's why symmetry is not such a crazy assumption.
Thank you.
I have a question about the termination decomposition, it looks like, if I understand correctly, you you separate the personal reasons from the market condition. Don't you
Yes.
think that personal reasons will also be affected by the market condition? If I have to buy a house, as an example that you gave, and the interest rate is low, it is less likely for me to terminate the annuity to buy the house. I might just go and borrow, in the markets, I assume the mortgage. So
Yeah.
would it be that C also in this equation that you showed depends on the interest rates that are prevailing in the market at the time of my choice?
Yes, this goes in here, but as I said, this modeling of surrender is quite difficult because the insurance companies, of course, have some data, but even their data is not good enough. They do not learn why people terminate the contract. So this basic C here as taking care of personal contingencies cannot be determined by using data. They don't give you the data, and they don't have separated data which shows you what is the real reason for termination. So it's expert knowledge. They have certainly some ideas why people terminate a contract, but this seems to be a reasonable way to take these two basic hypotheses into account: the interest rate hypothesis and the emergency fund hypothesis. But I agree, it's one of the most difficult issues here in modeling.
Thank you.
Please, some comments, questions? In such case, I would like to thank Ernst once more for his talk. And now I would like to speak about our program to the next Wednesday. On the next Wednesday, we will hear a talk of Ivan Alexeyev from St. Petersburg, and the title of his talk, Stable Random Variables with a Complex Stability Index. So now we can finish our seminar. Maybe Albert Nikolaevich would like to speak a few words.
Oh, Ernst, many things. And I am thinking about the following. Talk is very interesting, and you here is one, the great specialist. Maybe you, together with your co-authors, will write papers for our journal Theory of Probability. We are interested.
Yeah, but this is published already, so I cannot write a second paper on this topic.
No. I'm interested not only in the technique of this paper, second paper, but we need, in some sense, survey, paper of the survey character.
Yeah, maybe we can discuss it, but currently I'm busy with other issues.
Okay. No, in any case, many thanks. And you have, how to say, possibility to enter to our seminar, and we shall be very happy if you will attend. And many thanks again. Bye-bye.
Yes, thank you also. I want to wish you in particular good health in these difficult times.
Okay.
Thank you so much. And maybe for Russian participants, I will give an announce of the next seminar in Russian. Как я уже сказала, будет выступать Иван Алексеев, это ученик Натальи Васильевны Смородиной. И если до этого мы как-то слушали таких ярких, видных ученых, то, в общем, сейчас будет выступать такой талантливый молодой человек, который только сейчас начал обучаться в аспирантуре, как я уже сказала, с докладом «Устойчивые случайные величины с комплексным индексом устойчивости». Once more, I would like to thank all participants of our seminar, and now we can finish. Ernst, thank you once more.
Okay.
Владимир, я думаю, можно завершать.